just first say that I want to point out that I don't know how many of you are doing assignments. Well, hello, this is the last tutorial, right? So this is, I think, the last week of classes, right? Hooray or not, depending on your perspective. I kind of put for you guys tutorial 10 and 11. So tutorial 10 last week, as you guys know from the assignment, was based on multiple linear regression with categorical variables, and it was also based on functions in R. But then I kind of in the last bit talked about matrix algebra, right? So this is I did it in the context of least squares, and I don't know how many of you are doing assignment 10, but it might be helpful. But anyways, I realized when I was going over that tutorial, I didn't actually fully elucidate the operations very well. So if anyone was watching the YouTube video, they might have been a bit confused as to how is multiplying matrices. So this tutorial is kind of posted here, and it's me kind of, I don't know why it looks like this. Anyways, you can just copy and paste the tutorial, right? If you can, you can just copy this, although it looks awful. So I probably have to re-upload it. Anyways, let me see if I can do that now because I don't like the way it looks. I mean, I can't obviously, but I'll do that afterwards, right? So I think there's been an issue with how I committed my file because it looks kind of weird. Anyways, yeah, so I'm going to go over tutorial 11. You can copy it here, but it looks awful, so I'm probably going to recommit it afterwards. Yeah, so it's really this tutorial is going to go over how to actually multiply matrices. And you can obviously run this. You can commit this to HTML if you can knit to HTML if you're curious to how it looks. So there are multiple functions you can use for matrix multiplication and even for matrix algebra in R. But I tend to notice that the most common ones are actually these four, right? So obviously you have things like C-bind. So, you have things like C-bind, I guess I can put it in, right? So you have things like C-bind, which allows you to bind along the column of like vectors, and you have R bind, which you'll find yourself using when you want to create matrices from vectors, basically. Right. So when you want to construct the matrices, you're actually doing the matrix algebra on. You might find yourself using the last two functions, but the first four functions are really what you want to use if you're performing matrix operations, basically, right? So the first one is the most common, obviously. So in some sense, I've kind of actually put it in order of like the most common to least common, right? So these ones you use to create the matrices from the vectors, but here are the ones you use to perform the operations. Most common is obviously matrix multiplication, right? But you should not assume that it's always going to be the case that this runs if the dimensions of your matrices don't make sense, right? So we have to be a bit careful to make sure the dimensions match up in the way that it should. This is the operation for multiplication. So you have two matrices A and B. Then you have almost like a, like percent star percent is matrix multiplication, right? So you can imagine when you want to multiply two numbers in R, you just have star. So like, 3 times 2 will tell you 6, right? So if I just do this, it will say 6. So then when you want to denote that you're doing matrix multiplication and not scalar multiplication, you put the percent around the star so it knows it's doing matrix multiplication. So it's term by term within a scalar operation within the actual matrices, right? Okay, and then transpose, and obviously you can see is T of A, so it's like saying transpose. And by the way, these are functions, right? So if I put, for instance, transpose, it will give me the actual function. So, but if you want to know what the actual function is, right, in R, if you just put it into the console, it tells you what it's actually doing. And it's telling you that the actual namespace, like the environments you actually have this transpose function is not actually base R, right? So it's in something called per, right? So it's not actually base R, but nevertheless, it's embedded in base R, but the actual package was not actually built in base R. But yeah, so this is the function. So when you give it a matrix, it then transposes using this particular call here. Notice that you have the function, you have the argument section here, and then you have the body inside here. So akin to what we saw before, where you have the argument here and you have the body. So you put the matrix in here, then it's doing the transpose inside here in the body of the actual function. The same thing is true for solve, right? So you can see that when you look at solve, it's also not actually in base R, but this is actually inverse function basically. It's also it, right? So it's also not in base R, but this is actually right, only for matrices that are invertible basically, right? So you cannot use a solve function for non-square matrices, right? So intuitively, it's not even all square matrices that this solve function works on. It's only for those that are invertible. So if you take any, you know, n by n matrix where n is not actually invertible. So you just take, for instance, 1, 1, 1, 1, 1, 1, 1, 1, 1 for a 3 by 3 matrix, and it's all contains of entities that are 1. Well, you guys know that this has pivot 2. So it is not invertible because the last row could be expressed as a linear combination of the other two. Right. And in fact, actually, I think it only has pivot 1 because in fact, you only have one unique row, right? So it actually has pivot 1, not even pivot 2, right? So you cannot even find the inverse of that matrix, right? So it's really only true for those that are invertible, right? So what makes this function here obviously popular is you're going to use it, right? When you're doing least square solutions, the way in which you express beta hat, you have to solve for an inverse of a square matrix. So you need to use this function basically. So you actually use the first 3 functions. If you choose to do assignment 10, you probably won't use the last one, but I guess you could, if depending on how you actually set up your actual system. You may find yourself using the last one, but I don't think you necessarily need to. It depends on how you actually set things up, right? So I suppose in theory, you could use the last one if you set up your beta hat in such a way that you actually have 2 distinct, right? So if you have X transpose inverse times X times Y, you might find yourself using this solve function, but in general, you don't need it. You probably will find yourself first using the first 3, but the last one you may use depending on how you actually set up your system. But the last one differs from the first one in that, like, you're actually solving for, so if you have a system that looks like this, right? Y is equal to AX, right? And I guess I could probably put this inside the things that looks like this. So if you have a system you're solving that looks like Y is equal to AX, like this, right? You can solve for if A is invertible, you can find X basically. So what is the X that makes a Y a unique solution base? You may ask yourself, right? So Y is a unique solution if A itself is invertible. You guys know this from linear algebra, right? If not invertible, you may have infinitely many solutions, or you may have no solutions depending on how it's set up, basically, right? So what is the X that makes this system even solvable, right? And not just solvable, but actually a unique solution, right? Well, it depends on Y and X basically, but you can solve for this by if you have, for instance, an A, right? And you have and I guess this should be Y actually, right? So I should call this Y, right? So if you have a system where you have a matrix A is invertible and you have Y, you can solve this. This is what, see, the solve function is always going to be something that's unique to an invertible A. So if A is not invertible, you can't even really actually use a solve function, right? You can see how it's expressed here. It's really actually looking for an A that is uniquely invertible, right? So it's not just any A. Right, so it's the A where it actually has an inverse, and you know how matrix multiplication works. You have to, right? So if you want to solve for this, you would just put A on this. You take the A inverse here because A is invertible. So you know A times A inverse times A gives you identity basically. So you need to multiply it on the other side. So you have A inverse times Y, and you can solve for the system. Okay, so now let's see how this can work, right? If we kind of take some toy examples and systematically go in this way, right? So example 1. Is I'm going to construct a 2 by 3 matrix. So this is another helpful function you might find if you want to construct your matrix. If you want to construct a matrix for your, if it gives you a data set and you want to make a matrix yourself, you can obviously use this function, right? So I'm going to make a 2 by 3. You might say, how are you making a 2 by 3 matrix with this function? How do you know you're making a 2 by 3? Well, first of all, I specified that I wanted 3 columns basically. So if I put 3 columns, it means that if I only give, for instance, 6 values, it's going to recognize that to have 3 columns when you have 6 values is to actually only have 2 rows, basically. Right? So can I have 3 rows? If I have 3 rows, and that's me actually saying 2 columns, right? So it recognizes that if I put 2 columns, it's going to make this a 3 by 2 matrix, basically, right? So this is how you know what you're constructing. So think about this logically, right? So if I do this, it will make it a 3 by 2. So you have to think logically about what you're trying to actually perform, right? And ensure that your matrix is coming out the way you want to. Why is this? Because I just said that you guys know from linear algebra that it's not true that, you know, matrix operation is commutative, right? And by that I mean that, like, it's not even true. So by commutative, it means that we cannot say that AB is equal to BA, right? Because if A and B are not square matrices, you may not even have a defined operation, in the sense that, like, just because A, B is defined does not mean B of A is defined. And even if they're both defined, it may not actually be the same because, you know, if A and B are not inverses, we have no reason to believe that even in square matrices, where A, B, and BA are both defined, they should be equal, right? Unless they're inverses. That's the only exception which you kind of have this idea that maybe you have, like, right, the only situation where A, your matrix is actually diagonalizable, right? Or they're inverses, right? So there's only two instances where you kind of have some intuition that maybe they're the same, right? As in, like, you have a row, you just have row entries along the diagonal, but you have no other entries off the road. Maybe then you could say A, B is equal to BA, or they're inverses. But I can't think of a general situation in which I can say they're equal. In fact, we know that it's not true, right? So because of this, we need to be careful about how we actually construct our matrices, because it may not necessarily be defined, right, across all the operations, right? So I made this matrix. Now I'm going to actually make a matrix B, which actually is a 3x3. How do I know this? Because I provided 9 entries. So you see, I've provided 9 entries. So even if, so in this way, because when I run this, there's going to be, you can see, right, a 3x3 matrix, because I provided 9 entries and I asked for 3 columns, I'm going to get a 3x3 matrix, right? Now, of course, if you change the number of rows to anything less than 3, you're not going to get a 3x3. You're not going to get a square matrix, right? Because you provided 9 columns, and then you gave it a dimension that's, you gave it a number of columns that's less than 3. You're then getting an m by n that may not even make any sense, right? Depending on how you actually format the number of columns, right? So now I want to point out that the default is actually to append it by row equals false. When you put by row equals false, it means that, like, it's going to actually go across the columns. It's going to create column vectors. So you can see 1, 2, 3 is put in as 1, 1, 3. Sorry, 1, 3, 2 is put in like this. 1, 3, 2. And you have 2, 8, 9 is put in like this. And so it's going across the column space. If you, and because the default is row is equal to false, but so when it's row is equal to false, it's going to go across the column space. If you put something like, you know, by row equals true, then it's going to actually append it across the row space, right? So actually we can construct a different matrix to see how this can look, right? So let's say I put like B2 is going to be equal to, you know, matrix, and I'm kind of going to just copy and paste this because it's so much easier. Then I'm going to put by row equals true. So if I just, you know, copy this matrix and do something like, you know, by row equals true, and then I put B2, we'll look and see how it differs, right? So now you can see that in the second instance, it's going across the row space. So instead of doing 1, 3, 2 like this, it goes 1, 3, 2 this way, and it's like literally transposing your matrix basically, right? So it turns out that in this way, right, if you take B2 to be equal to the transpose of B, you're going to get the same matrix as what I did, right? So in some sense, this is, you know, akin to a transpose. Let me put this here. This is a transpose, right, of B. So if you take, for instance, transpose of B, you might get it's fully equal to B2, right? So if you double check yourself and see, right, that it's doing that, right? And I guess that's another way in which you can actually construct matrices. If you realize you messed up your matrix, you don't want to go back and you forget that you can do by row equals true. You can just take the transpose of B and it will correct your matrix for you basically. Right. Okay. So like I said, we can multiply in one direction, but it's not commutative basically, right? So first of all, they're not both square matrices, so it's not even truly the case that they're both, that BA is defined in the same, right? It's not in this instance here. Only AB is defined, but unless they're inverses or diagonalizable, we should not say that, right, that they're the same. Okay, so now let's see. So again, we know that matrix multiplication has the percent sign around the star to make it clear that it's not scalar multiplication, it's in fact matrix multiplication. So if we do this, what do we get? Oops, why is this doing that? What is, I probably messed up something. Dimension of A is, let's say it's 2 by 3. The dimension of B, it should be 3 by 3, so it should work. Let me see. Oh, it's because I'll tell you why that happened in a second. That happened because when I actually try to show you what happens if you put by row equals true, it changed it to something else, but it should work though. It's so weird. Yeah. So the reason why is because when I was up here showing you guys what happens if you change this, it looked like this. So it changed, instead of looking like this, it changed it to be the 3 by 2, right? So when you have 3 by 2, it doesn't run, right? So it stored A as 3 by 2, because I was showing you guys what happens if you change the number of columns to be 2, and then it didn't make sense, right? It was saying that it's not defined. So when you get the argument, that's a good thing to note that when you get something that says like your thing is not conformable, it means that you made a mistake and you probably have dimensions that don't make sense. So when you get the dimensions not conformable, go back and look at the dimensions of your matrices. You probably made a mistake there. Right? And this is going to be important for any of you, even if you don't do this assignment, but some of you find yourself doing something like, like next semester you do D37, or not next semester, but in the fall or something. Then you probably will need to know these kind of things, because D37 will heavily rely on matrix multiplication. So you'll see yourself using it a lot in your assignments. Okay. So now let's look at how to use transpose. This one's pretty simple, right? And in fact, I realized it's kind of silly of me because I could have done like, when I take transpose of A, I get the following. So I get the 3 by 2, right? But I could have also showed you guys that, like, if I take the transpose of, like, let's say B, right? Subtract that T of B is, right, equal to B2. I could have done that as well. And let's see what we get. So you can see that if I compare what I have here, so this is 1, 3, 2, 2, 8, 9, 2, 3, 4. It looks the same basically, right? So it is a case, that's because I said by row, so it's doing the transpose basically. And so this is the transpose function. You will use this in your assignments, right? Because when you construct X, you're going to take the transpose of X to construct X transpose X. So you eventually will need to use this function. And it's very intuitive in the sense that, like, obviously T denotes the transpose, right? So it's very natural label for the function in some sense, right? Okay, so let's see how taking the transpose will change the way in which we perform matrix multiplication, right? So now, remember, I said that we cannot do it. We said that AB is not defined. Sorry, we said that BA is not defined. So BA is not defined because, of course, we had that, B is a 3 by 3. And we have that A is actually a 2 by 3. So if you want to do B times A, this can't work, right? Because you have the inner dimensions are 3 and 2. It's not even defined. But if you take the transpose of A, now you have 3 by 2. And this is a defined thing because the inner dimensions are 3. So of course, this should actually conform, right? So in the way that, like, B times A does not conform, it should be the case is conformable. And it does actually give us another 3 by 2 matrix, right? So these are little things to check for when you're just like as when you're asked in a linear algebra exam to take a pen and paper and matrix multiply, and make sure you're making sense of your multiplication in R as well. Okay. Let's solve the system now. So I'm going to show you guys that, of course, this is so this is the R-bind function. You really use R-bind in contrast to, or instead of, let's say, for instance, matrix. If you're in your assignment, you're not constructing. So you see here, the reason why I use matrix here instead of R-bind is because I'm making up numbers basically, right? So I don't have vectors that are already pre-assigned for me. But let's suppose in your assignment, you instead of having like numbers, you actually have variables that you need to append together to make matrices. that's when you might use C bind and R bind. So in your assignment, he might give you a data set, and instead of using numbers where you make the matrix yourself, you may need to actually use R bind and bind the vectors in an appropriate way to make your matrices, right? So that's when you might use R bind and C bind in your assignment instead of using matrix. All right, so that's why I made it up here. So you can see here, I'm actually binding scalars, but I can bind vectors based. So let me make a note here, right? So note, I am binding, scalars, but of course I cannot obviously bind, vectors as well. But when you do this, think about the way in which you're actually binding, right? So you have to think about the output, the vector the matrix you want to actually make. So here I've made a vector, right? So this creates a vector. Oops. This creates a vector, right? But you need to think for yourself as to, right, to create matrices. But like I said, think about what you wanted to actually construct in your matrix. So this would determine if you should use an R bind or a C bind, because when you run the actual code and have a look at your actual output, if it doesn't make sense, if the dimensions don't make sense, it's probably the wrong bind. By that I mean it like, when I do an R bind, I'm going to get, because it's binding across the rows, it's going to give me a column vector, right? Because it's going to say 2, 4, and 6, and it's going to create a column vector. So this is going to be a 3 by 1 vector. So that means that I have to think about how I'm binding it with, I need to think about how I'm binding it basically, right? Because this means that I can only multiply by things that are obviously itself a scalar on the left base, on the right basically, right? But on the left, I can multiply by things that are 3-dimensional base. So I need a 3 by 3 or something, or 2 or whatever, 2 by 3, whatever you have the 3 of the inside. So we need to be careful about this because you may not be able to conform your arguments if you bind in a way and you try to do matrix multiplication, it doesn't make sense, right? So you can see that this creates obviously the column vector because it's binding across the rows. Now, in your assignment, you may be binding, like matrix, you may be binding vectors, so you'd have extra numbers. So you'd have 2, maybe you have 2, 4, 6, 4, 7, 9. You keep because you're binding across the rows, you'll get like a matrix of some sort, basically, instead of a vector. Now, let's suppose I want to solve the system. So this means I'm going to do examples 3 and 4 here, right? So example 3 is finding the inverse. Example 4 is solving a system. Now, first of all, I can check to see if I didn't even know if I did not know initially when I constructed B, whether or not it was invertible or not, but I can check obviously, because if I put my B into my solve function, it tells me not conformable, or it tells it cannot, it's singular. So it'll tell you that B is singular, right? So let's actually see if this is true. Let's say C is equal to matrix of, let's say, I don't know. Let me just make sure I'm doing it correctly. So let's say I just put a bunch of ones basically. So I need to put my column back, and let's suppose I just put 1, 1, 1, right? And then I just put 1, 1, 1. I should have 9 of them. So I have 6, 1, 1, 1. So, so let me see. It's CTES. So this is not what I want. So I actually really want to make it square matrix. I forgot to put number of rows equals 3. So as you can see here, full disclaimer, if you don't put the number of rows, we'll just give you a vector, which is not what I wanted, right? So number column equals 3. Now let's suppose, so now you can see that it does this. Now, if I do solve of C, it will say it's singular basically. It cannot work when it's not invertible. Now I know it's not invertible because the last 2 rows can be expressed a linear combination of the first one. I only really have 1 pivot, right? So this is something to keep in mind, right? So there are 3 variables here because there's only 1 unique row, right? So you cannot solve a system if you have a singular matrix. So just if Ken asks in your assignment to solve and you go to something that's singular, you may have made a mistake somewhere. So go back and double check your work, right? So now I know that B is obviously invertible and that means it has full rank, right? Because when I solve it, basically, I get a solution, basically. Okay, so this is how I know that B has full rank. It has 3 pivots. And so I can then, and now this is important. Why? Because if I want to solve the system, and you may find yourself doing this in your assignment, I need to make sure that it's actually even possible to get a unique solution, right? So I cannot get a unique solution, right, if it's not invertible. So now let's be careful here. Because I know that y itself is actually a 3x1 vector, and I know my matrix B is actually 3x3, right? This is why it looks the way it does. So I have 3x3, and I have 3x1. Notice that these inner things is actually a defined thing. So I can actually, this solve function is going to actually multiply these two things together, and it's going to find it's going to find the inverse, right? It's going to find B inverse, and it's going to multiply it by y. It's going to multiply the inverse of B by y, and it cannot do that if the dimensions don't make sense. So if I constructed, right, a y vector that was actually by C bind, if I use C bind to construct y, it will create a row vector, and it will not actually run. So when I put solve of B of y, we'll say it doesn't make any sense because it's a 1x3 vector I've created, which does not make sense. But I can fix that, of course, by taking the transpose. So let's actually see if this is correct, right? If what I said is true. So let's suppose I say something like, actually, let's call it aside. So aside, let's fiddle and see what happens if we tried this with a C bind vector, right? So I'm going to construct a new vector. Let's call it Z is equal to C, let's say, and let's make it the same vector. So 2, 4, 6. So let's make it, so instead of R bind, I'm going to do C bind of 2, 4, 6. And what I get, right, is, and I put C. I get this row vector, right? So now if I want to actually solve, right, for B, Z, it may not actually work. You see, it says it's not compatible base. You cannot have a 1x3. It's not compatible with 3x3. So you have to be a bit careful here. Right? So this will not run because it's recognizing you cannot do this operation basically. Right? This doesn't make any sense because these inner two things here don't match. So it's saying that this is not something we can actually work with. We need to think logically about our operations basically. Right? But what you could do, okay, so this, let me just put a note here, this will not run. So right? As 3x3, 1x3 is not conformable. Right, but what you could do is you could take the transpose of this. Now, what will run? Solve of B, right, and T of Z, right? So this should be able to run, right? This gives you this, and it probably gives you the same output you get with this because you see it's created. It now takes the column bind to row bind, and you get the same answer. Right, so if you made a mistake somewhere, there's always multiple ways in which you can actually go back and amend yourself, right, to get the appropriate thing. So these are the kind of manipulations you'll use for assignment 10. And I need you doing assignment 10 out of curiosity. Like any of you want to replace one of your grades that you didn't like, just out of curiosity. Let me see how many of you are going to change your, let me see how many of you want to actually go back into the assignment again. So most people probably won't, but I still encourage you guys to do it, just for your own sake. I mean, probably most of you are happy with your marks, and that's cool too. If you have other final exams you want to study for, that makes sense to prioritize those. But these will still be really important for you if you guys take D37. Are any of you doing D37 next fall? Or I guess some of you probably took C67 this semester, but you probably won't be doing this kind of stuff in C67. Where you will see it is in D37, which is multivariable regressions. That's when you start looking at like multidimensional regressions. That's when you might use this stuff. Any questions about this? Otherwise, I guess that's pretty much it for today. It's going to be a short tutorial just because there's really not much to necessarily take up. But if anyone has any questions, I'll kind of ping back. Otherwise, have a great rest of your day, guys.